In my presentation today, I will share some developments on liquefaction triggering resulting from our research in the last few years. It is interesting to know that Drs. Martin, Finn, and Robertson, who gave 3 of the last 4 lectures, also focus on liquefaction, showing how much this continues to be a significant issue for the geotechnical community. Now, when we talk about liquefaction, and especially liquefaction triggering, we're all building one way or another on what Professors Seed and Idriss did when they published their magnificent paper in 1971 on the simplified procedure. The method had stood so well the test of time that any new development on triggering tends to occur naturally within the framework of the simplified procedure. This is certainly the case with the findings I will be presenting today, which are either extensions or proposed modifications of the simplified procedure. I also want to acknowledge the people and organizations listed on the screen for their support and help in preparing this lecture. Lots of people, I'm not going to read all their names. I am not shy. Whenever I am in trouble, I reach for the phone. Lots of people to say thank you. But let me add special thanks to 6 key people who played a major role in my professional career by mentoring my initial research efforts many years ago. They are Arturo Arias in Chile, Enrique Tamés in Mexico, and Bob Whitman, John Christian, Jose Roset, and Eddie Idriss in the US. The 3 photos on the screen correspond to liquefaction effects on sands in New Zealand, San Francisco, and Haiti. Liquefaction occurs in many large earthquakes with devastating effects, and it is also a very complex phenomenon. These are the 2 main reasons why it keeps coming back at us, and why we're still working on it after half a century of research. These 3 photos illustrate the consequences of liquefaction during earthquakes. My focus today is not necessarily on those consequences, but rather on the triggering of liquefaction in level or almost level sites, with the consequences typically happening only after triggering has already happened. There have been a number of triggering liquefaction charts proposed over the years based on the simplified procedure, all calibrated by field case histories of liquefaction and no liquefaction, typically normalized to earthquakes magnitude 7.5, and having the common format you see on the screen. Many of you are very familiar with these charts. The 3 main properties used to measure liquefaction resistance are standard penetration resistance, or SPT, which I am not showing, static cone penetration resistance, or CPT, in this chart to your left. I don't know if I can point from here. The angle is not propitious. Okay. And shear wave velocity, or VS, in the other chart to your right. The parameter along the y-axis of all charts that defines the seismic demand on the soil is the same in all of them, the cyclic stress ratio, or CSR. Let me add a couple of comments about the 2 charts on the screen. The CPT measures penetration resistance, so it is a large strain field test, while V/S measures the soil shear stiffness at very small strains. Also, the case histories used to calibrate this particular CPT chart are all clean sands, and therefore the chart is only valid for clean sands having less than 5% or 6% fines. For silty sands, Idriss and Boulanger and other authors have developed for the CPT as well as the SPT a fines correction, which increases with the amount of fines and which is added to the measured penetration resistance before entering the chart. This added resistance can be quite substantial. For the VS chart, the situation is simpler, with the chart being essentially independent of the fines, so no correction is necessary. In the year 2000, Andrus and Stokoe tried to establish a difference by plotting these three curves, which I will point to you if I could, but I cannot, which depends on fines content. But as you can see, the three curves are very close. And a more recent study by Kayen and his co-workers definitely proved that no fines correction is needed in silty sands, at least up to 35% fines when a shear wave velocity chart is used. My final comment about these charts is the special role played by the cyclic stress ratio measured along the y-axis. This CSR is the seismic demand calculated for all the data points used to calibrate the charts, corresponding to sites that have liquefied or have not liquefied. It is also the Y value you will use to plot your site when evaluating liquefaction potential for your design earthquake. CSR is a measure of the cyclic shear stresses imposed by the earthquake on the liquefiable layer, and it is usually calculated from the peak ground acceleration of the earthquake. Now, due to the difficulties involved in trying to define the ground acceleration at a site which is liquefying, in the simplified method, this acceleration, as well as the CSR, are defined not for the actual site and layer, but instead they correspond to a fictitious similar site, equal in every respect to the original one, except that it does not build up pore pressures in any layer and is assumed not to liquefy for the purpose of estimating CSR. This is equivalent to assume that the seismic shear stress and strains acting on the liquefiable layer are not affected by the strain softening, which invariably occurs during pore pressure buildup and liquefaction. For the sake of simplicity, the method neglects this softening of the liquefiable soil layer induced by the pore pressure buildup. And all your calculated accelerations, shear stresses, and shear strains are index properties without physical meaning if the soil liquefies. In other words, if the point of the chart corresponding to your site plots below or on the curve, that is point A or point B in the figure, these calculated values of CSR, shear stress, acceleration, are reasonable representations of the actual values developed in the soil during the shaking. On the other hand, at point C, the calculated CSR, shear stress, acceleration, strain, have little to do with the actual values. And in this case, CSR is an index parameter without physical meaning for the site. I'm not criticizing this at all, just clarifying the issue because I will need to come back to it later in the talk. In fact, this simplification seems to be unavoidable in the process of making the process truly simple and friendly to use by practicing engineers. This is the outline of the rest of the talk. I will start with a review of some key liquefaction issues in the 1970s. That shows you how old I am. I mean, I was reading papers at the time, which culminated in the 1980s in a consensus about the basic mechanics of pore pressure buildup and liquefaction, where, in fact, Professor Seed played a major role. Then I will describe our 5 research findings one by one. I will also spend some time developing a key equation I need for most of the findings between the cyclic stress ratio CSR that we just discussed and the cyclic shear strain gamma sub C, which is an alternative parameter to CSR that also describes in a different way the demand imposed by the earthquake on the soil. Let me say a couple of things first about the basic liquefaction studies in the 1970s before I move to the next slide. The main breakthrough was a model developed by Martin, Finn, and Seed that related densification of a sand subjected to cyclic shear loading in drain condition to the increasing pore pressure in the same sand due to undrained cyclic loading. I don't have time to get into the details of this model. Let me only say that the model was verified by several laboratory studies in the 70s and 80s. And very importantly, from my viewpoint today, it told us that the best way to understand pore pressure buildup at a basic level is to look first at what happens to densification of dry sand subjected to cyclic loading. So, let's look at densification of dry sand subjected to cyclic shear. An excellent study of this was done also in the 1970s by Silver and Seed at the University of California, Berkeley. They used a device which was not quite identical to the direct simple shear sketch on the screen, but which provided similar boundary conditions. As you can see, what we have is essentially a consolidometer with rigid walls used to compress the dry sand under the vertical pressure sigma sub V. Except that the rigid walls are hinged at the bottom so that they can also rotate back and forth in order to apply cyclic shear loading under constant sigma sub V. This cyclic loading that can be quantified either by the applied cyclic shear stress tau sub C, that I would love to show you if I could, or associated cyclic shear strain gamma sub C, produces in turn the sand densification measured by the settlement of the top S and permanent vertical strain epsilon sub V. And here you have the actual traces measured in the first few cycles of one of the tests conducted by Silver and Seed, with the shear loading applied at constant vertical pressure. A constant cyclic shear stress was applied tau sub C, which generated also a constant cyclic shear strain gamma sub C, as there was no stress-strain degradation. Therefore, these experiments can be interpreted as being either stress-controlled or strain-controlled. It's your pick. The top trace shows the development of the permanent vertical densification strain epsilon sub V, which accumulates cycle after cycle. And here are the plots summarizing their results from several tests. The data correspond to densification measured after 10 cycles of a given tau sub C. The densification increases when the cyclic shear stress tau sub C increases, no surprise here. And for a given cyclic stress, densification decreases when the sigma V of the test is greater. But the most interesting plot is this one, where the same densification is plotted instead versus the cyclic shear strain of the test. As you can see, in this plot, the results collapse into a single curve which is independent of confining pressure. That is, Silver and Seed discovered that densification after a given number of cycles, given sand, relative density, etc., is independent of effective confining pressure and therefore of depth in the field if the cyclic shear strain is used as parameter instead of the cyclic shear stress. On the basis of this finding on densification, together with a close relation between densification and pore pressure buildup found by Martin, Finn, and Seed, a group of us that at the time included also Richard Ladd, Jen Stokoe, and Les Jaud, proposed to use cyclic shear strain instead of CSR as a basis for a new generation of liquefaction charts for field evaluation of liquefaction potential. Between other things, this would have brought into the picture the shear wave velocity, which is a measure of the shear stiffness of the soil. It was quite a radical proposal, and also premature for the tools available at the time. But hey, why not? We're all young and ready to change the world. The important thing from the viewpoint of my lecture today is that as a result of that discussion, a consensus developed which was beautifully summarized in a statement included in a paper by Seed, Idriss, and Arango. I have labeled this statement the consensus of the 80s, which in my opinion is still completely valid today. Let me read the complete statement. Quote, "In reality, however, Liquefaction is a phenomenon which results from a tendency for volume change in a sand due to the application of cyclic shear strains, Martin, Finn, and Seed, 1975. And volume changes are more uniquely correlated to cyclic strains than cyclic stresses, Silver and Seed, 1971. It has often been suggested, therefore, that the development of a correlation between the cyclic strain induced by an earthquake and field performance might provide an improved basis for liquefaction assessment. Dobry, Stokoe, Ladd, and Yao, 1981, the 4 young musketeers then. There is no doubt that such an approach is appealing because of its more fundamental basis, and the writers considered this possibility some years ago. End of quote. Now, please note that by the 1980s, and as this quote says, Seed and Silver had demonstrated that densification is more uniquely related to cyclic shear strain than to cyclic shear stress. We assume that this was also true for pore pressure, but I am not quite sure this particular issue was completely settled at the time. But it was certainly settled quite definitely, in my opinion, a few years ago, in one of our own projects, as I will show you in a minute. Which brings me to our finding number 1, numero uno, defined as the answer to the following question. Is excess pore pressure more uniquely related to cyclic shear strain than to cyclic stress ratio? The answer to this question emerged from a series of 4 centrifuge tests and 2 large-scale tests conducted at RPI and at the University at Buffalo under the direction of Professors Abdoun and Tevanayagan. What you see on the screen is one of the 4 centrifuge tests conducted on a silty sand with 21% fines, having a relative density of 35%, and placed as a uniform deposit 6 meters thick in the prototype. The 6 deposits we tested included both inclined and level cases, and the inclination did not make any difference in the pore pressure results. The model deposits were instrumented with piezometers, accelerometers, and other sensors mostly embedded in the soil. The deposit was subjected to these 10 cycles of constant amplitude acceleration at the base. The peak base acceleration in this and the other tests was only about 0.02 g, small acceleration, as the purpose was not to liquefy the soil, but to generate enough excess pore pressure short of liquefaction so we could study the pore pressure buildup as it approaches liquefaction. Here, I'm pointing to it, right? You have the excess pore pressure ratio recorded in this test by the shallow piezometers, where the pore pressure ratios were greatest, which by the end of shaking had reached a pore pressure ratio of about 0.4. Significant, but still far from liquefaction triggering that would occur at a pore pressure ratio of 1.0. All 6 deposits of loose sand had the same prototype thickness of about 6 meters. They were all subjected to the same base acceleration. But there were also 2 differences. One, some tests were done with this silty sand and the others with clean sand. And 2, we used dry pluviation in some of the tests and hydraulic filling in the others, therefore creating 2 different types of soil fabric, with soil fabric influencing significantly the results. By covering this range of sands and soil fabrics, we started approaching the diversity of conditions we find in the field. Because the pore pressure buildup was limited in the 6 tests, there was not much stress-strain degradation. So we could process the horizontal acceleration records at different depths using system identification to extract the shear stress time history, tau, at mid depths in the deposit, which is this trace here, with a peak shear stress of about 2 kPa. Similarly, we could extract the shear strain gamma at the same depth, which is this other trace here with a peak shear strain of 0.03% or 0.04%. As you can see in the two traces, there is essentially no stress-strain degradation, except perhaps a little bit near the end of the time history of gamma, where there is some starting. Therefore, this centrifuge experiment can be considered either as a test of constant cyclic shear stress tau sub c or constant cyclic strain gamma sub c, where this single value of stress or strain can be used to represent the whole time history. We selected gamma sub c and tau sub c as the median of all 20 peaks or so in the corresponding time history. Here you can see the peak selected for gamma sub c, and here is the peak selected for tau sub c. These two selected values of gamma c and tau sub c correspond to different peaks. With the method we used, there was no reason for them to happen in the same peak, and it doesn't make too much difference anyways. Finally, we obtained from this selected tau sub c the value of the cyclic stress ratio, or CSR, of the test by just dividing it by the effective vertical pressure at that depth. And here you have the first graph, where we plotted the maximum pore pressure ratio RU max measured in each of the 6 tests. These 6 data points are 1 test each, versus the cyclic stress ratio of the test CSR. The plot does not show any particular correlation between the two parameters. And here you have the corresponding plot for the same RU max, but plotted now versus the cyclic strain of the test, where the correlation is much better. In fact, it's quite good. We find here for pore pressures the same zinc, silver, and lead found for densification of dry sand, that the pore pressure is much better correlated to cyclic shear strain than to cyclic stress ratio. Let's focus on the plot on the right. For the two tests which had a gamma sub c less than the threshold strain at about 10 to the minus 2%, there are 2 data points there which show no pore pressure buildup at all in the sand, as expected. While above the threshold, there is a fast increase in RU max as gamma sub c increases, with values of pore pressure ratio between about 0.4 and 0.7 at a strain of about 0.025%. We also computed for the 2 plots the coefficient of correlation, usually called R in the statistical literature. And as you can see, it is 0.89, close to 1.0, corresponding to perfect correlation for the strain plot, and only 0.07, close to 0, corresponding to no correlation for the CSR plot. Therefore, here is our finding number 1. Pore pressure ratio is more uniquely correlated to gamma sub c than to CSR. The next step is clearly to investigate what is the level of cyclic shear strain gamma sub c associated with liquefaction in the field during actual earthquakes. We can do this by going to the liquefaction charts, which after all have been calibrated by field case histories. The charts, however, use CSR. So we first need to find an equation to calculate gamma sub c from CSR for any point of the chart. I will develop that equation in the next few slides. Okay, here we go. We have this liquefaction chart. Let's say the original Shear and Idriss chart based on the SPT. And we want to know the value of the cyclic shear strain gamma sub c for this point P on the chart, for which we know 2 things, CSR and the normalized SPT, which is N1. At the top are the 2 main definitions of CSR. The one mostly used by practicing engineers, which use the peak ground acceleration A sub max. And the second, more basic definition, where CSR is defined as the ratio between the representative cyclic shear stress in the layer tau sub c normalized to the effective overburden pressure before the earthquake, sigma prime V0. I am going to develop the equation between CSR and gamma sub c using an animation, which is nice. I mean, it's distracting, fun, like going to the movies. I will also go fast, but this should not be a problem, as most of you are very familiar with the plots, symbols, and intermediate expressions I will be using. We just switched to a shear wave velocity chart, like, for example, that proposed by Andrus and Stokoe, with VS1 at the bottom instead of N1. Can we do this? Of course we can, if we have measurements of both SPT and VS at the site. Okay, this is our starting point. Let's now begin our derivation, where we will convert this definition of CSR into an equation relating CSR to gamma sub c. We go back to the classic hysteresis loop, which you have seen many times if you ever took a solid dynamics course, where tau sub c and gamma sub c are defined as the coordinates of the tip of the hysteresis loop for cyclic shear loading of soils, including sands. G is the secant shear modulus, which is tau sub c divided by gamma sub c, and G max is the value of G at very small strains. Therefore, this is true, and this is true, and therefore we can replace. Nice, isn't it? And gamma sub c has made its dramatic appearance, its first appearance. But of course we have the G here, which we don't know what to do with it. We have to transform it into VS somehow. And for that we need a couple of steps. The first step is we go to the modulus reduction curve, which you have seen many times, which means that if we know gamma sub c, we know also G over G max, and therefore this is true, and we can replace. Okay, we have gamma sub c, G over G max c, which is a function of gamma sub c, and we have G max, and we have sigma prime V0, which you should know for your site and layer. And to replace G max sub c for VS, we go back to theory of elasticity. Under certain conditions, this is true. G max is rho VS squared, where rho is the mass density of the saturated sand. And therefore, we replace, and we are almost there. All we have to do now is to replace VS by VS1, its normalized version, for which we go back to the definition that Andrus and Stokoe provided for that. Sigma prime V0 is in kPa, and therefore this is true, and we replace, and this is the equation. We simplify it a little bit, and we have this final version, where if we know CSR and we know VS1 and a couple of other things we should know, we can calculate gamma sub c. Armed with this equation, this is the equation, we can now go to the liquefaction chart and find out what is the actual level of cyclic shear strain that is needed to trigger liquefaction in the field, as shown by the case histories in the field for which the charts are built. Here you have the same Andrus and Stokoe VS1 chart you saw before. And I have also superimposed the more recent curve proposed by Kayan and his coworkers. It gives the same results. Using the equation I just derived between CSR and gamma sub c, we computed the cyclic shear strain needed to trigger liquefaction, which we labeled gamma sub CL at the two ends of the Andrus and Stokoe curve. We obtained the value shown in red for gamma sub CL, about 0.03% at the low end of the curve, and 10 times higher, about 0.3% at the higher end. Let me add that Sid, Idriss, and Arango, in the same 1983 paper I quoted before, also estimated the gamma sub CL corresponding to their SPT curve at the time, using a correlation between SPT and V sub S, and arrive exactly to the same value of 0.03% we have here, which I find a truly remarkable prediction made 30 years ago. So, our finding number 2 is that triggering of liquefaction in sands in the field during earthquakes occurs at small to medium strains ranging from about 0.03% to 0.3%. I think this finding should be used by the profession to reassess some of the things we have been doing historically. For example, does it make any sense to try to use critical state theory to understand triggering when considering that critical state applies only to much larger strains than this? Or should we still be using result of stress control cyclic triaxial tests for triggering evaluations when the strains at the end of the test sometimes reach 3% or 4%, too large to be relevant to the triggering phenomenon? Food for thought. Let me say one more thing. The lower branch of the liquefaction chart, where we have the 0.03% or so, is known to be controlled by recent loose fields and natural sands. So, we decided to explore the hypothesis that recent uncompacted artificial fields have their own liquefaction chart, defined by a constant gamma sub Cl of about 0.03%. But what is the shape of this curve of constant triggering strain when plotted on a liquefaction chart? Well, here is the same equation I derived before between CSR and gamma sub C, which can also be written in this other form as a function A of gamma sub C times Vs1 squared. That is, for constant gamma sub C, CSR increases with the square of Vs1, and the curve is a parabola. And this brings us to our finding number 3. We took all case histories in the Andrus and Stokoe database that were uncompacted recent artificial fields, and were also either clean sands or silty sands up to 35% fines. And we plotted them on the same chart of CSR versus VS1 for earthquake magnitude 7.5. We also included, as additional case histories, the centrifuge and large-scale tests I showed you before. And we were able to fit this constant strain parabola having the equation you see in red. CRR, which is the value of CSR for points on the curve, is equal to 0.033 times VS1 divided by 100 all squared. You can see that this strain-based curve separates very nicely the cases of liquefaction from no liquefaction, and corresponds as expected to a triggering cyclic strain of 0.03%. So, our finding 3 is that liquefaction triggering of recent uncompacted fields with fines content up to 35% is explained by a constant cyclic shear strain curve, with the strain being 0.03% for an earthquake magnitude 7.5. The plot thickens. Okay, let's go back to the original Andrus and Stokoe chart you saw before, which you see again on the left. The data points in this chart include a number of what have been called false positives, that is, sites that should have liquefied because they are above the curve, but in fact did not liquefy. All these open circles you see here inside this red oval are false positives. Well, we found out that most of these false positives they are not random data points. They are naturally deposited, geologically young, silty sands located in a very specific part of the world, the Imperial Valley of Southern California. The map to the right shows the valley, and the 4 red dots shows the location of the sites which provided all case histories in the Andrus and Stokoe database. A main feature of the Imperial Valley is that there are a number of active geologic faults and a lot of earthquakes. And this constant shaking seems to be the main reason why these sites have a higher liquefaction resistance than expected, based on their values of VS1 and the Andrus and Stokoe chart and the KN chart, both charts. For example, at one of these 4 sites, the liquefiable layer in the wildlife site I just named, that layer seems to have been deposited in 1907. That is only a century ago. So it is younger than some of the artificial fields in the San Francisco Bay Area that liquefy extensively in the 1989 Loma Prieta earthquake. However, in 2010, this wildlife site was subjected to an earthquake comparable to Loma Prieta, which generated only a small pore pressure in the liquefiable layer. So, again, we took all case histories in the Andrus and Stokoe database located in the Imperial Valley, which were either clean or silty sands up to 35% fines, and plotted them on the same CSR versus VS1 plot. We were able to fit this parabola, the solid line, separating liquefaction from no liquefaction, which corresponds to a cyclic strain much greater than the 0.03% we had found before for the uncompacted fields. That is, the cyclic shear strain needed for triggering in the Imperial Valley sands is of the order of 0.1 to 0.2%, 4 times greater. With the corresponding solid line parabola playing much higher than the parabola for the uncompacted fields, which is shown on the screen by the dashed line below. In fact, the CRR, the liquefaction resistance needed for triggering in the Imperial Valley, is almost exactly twice that of a recent uncompacted field of equal VS1, and this is our finding number 4. This would explain the false positives of the Andrus and Stokoe chart by heavy preshaking due to previous earthquakes. It also suggests that a given family of sites and sand layers subjected to a similar geologic and seismic environment, like in this case, may be characterized by a regional liquefaction chart corresponding to the level of cyclic strain that reflects this particular environment. To understand better what happened, we focus on the liquefiable layer at the wildlife site, which seems to have been deposited by flooding in 1907. So the layer must have had a fabric similar to the hydraulic field immediately after deposition. Then we took a comparable silty sand site in the San Francisco Bay Area, the Treasure Island Fire Station site that did liquefy in 1989, and which had been deposited artificially as a hydraulic field in the 1930s, that is half a century before the earthquake. Dr. Steidl, a seismologist at UC Santa Barbara, helped us understand what happened. He went to the earthquake catalog and counted a total of about 61 earthquakes, producing a peak ground acceleration greater than 0.10 G at wildlife between deposition and the 2010 earthquake, when the site had a shaking similar to Loma Prieta, but did not experience liquefaction. Dr. Steidl then repeated the same earthquake counting for the Treasure Island site and found that there had been only 2 earthquakes of more than 0.10 G between deposition and the Loma Prieta earthquake, which seems to explain why at Treasure Island the layer still behaved as a recent sand field in 1989, while at wildlife the layer behaved as a heavily preshaking sand of increased resistance in 2010. We decided to investigate further the influence of preshaking on liquefaction resistance through a series of centrifuge and large-scale experiments. We did 3 centrifuge tests and 1 large-scale test using 2 sands, a clean sand and a silty sand. In all 4 experiments, we placed a deposit of about 6-meter thickness and subjected it to several dozen shakings using different patterns and simulating in an idealized way the seismic history of a sand, located, for example, in the Imperial Valley or in another very seismic area. Experiment 1 that you see on the screen is the one that approached most closely, but still in a very crude way, the situation at wildlife. Specifically, we applied a total of 66 shakings, of which most corresponded to this short duration A, the one with 5 cycles at the top. And a few shakings correspond to this much longer duration, 15-cycle duration event B. Events B, fewer in number, were expected to liquefy the deposit, at least at the beginning of the test, while events A, many of them, represent the many local preshaking events that have been observed at the site, which typically generate pore pressures, but not liquefaction. Here you see the sequence of the 66 shakings in this experiment 1. The ordinate of the plot is CSR 7.5, normalized to 7.5 magnitude earthquake, in order to account for the different durations of events A and B. Events B are the blue vertical lines, 6 events in total, and the events A are the 60 black vertical lines. This bottom plot shows for each of the 66 events the maximum pore pressure ratio measured anywhere in the deposit at the end of shaking RU max. This is a fascinating plot. The first event B, labeled shaking 1, number 1, induced an RU max of 1.0, liquefying the deposit. The first blue dot at shaking number 1. 50 events later, or 56 events later, shaking number 56, which is also a blue dot, is also an event B, did not induce liquefaction with RU max being 0.6. This event B, shaking 56, is of special interest as it approaches the situation at wildlife at the time of the 2010 earthquake, which also did not cause liquefaction. The pore pressure responses for event A, which are the black stars, are also illuminating. The pore pressure ratio decreased fast within any sequence of 10 events A. I can show you this, but jumps to a much higher value immediately after an event B. And then it starts decreasing again, canceling the effect of the event B after 2 or 3 events A. Therefore, this is, in terms of liquefaction resistance, is a 2 steps forward, 1 step backward process, with a net result in the long run of a significant increase in liquefaction resistance. You can see that the events A have much higher pore pressure ratios between events 2 and 12, 2 and 11, than between events 46 and 55. I mean, the net result is an accumulation of an increased liquefaction resistance. We measure the shear wave velocity of the soil between events with bended elements, and the pattern is extremely simple and baffling. While the liquefaction resistance was varying dramatically, going up and down, but with the sun being clearly stronger after 50 or 60 shaking, the shear wave velocity almost did not change. The value of VS1 of the silty sand was about 100 meters per second at the beginning, and it was still 100 meters per second at the end. And this brings me to our finding number 5, which is the answer to the following question. Is the CPT more sensitive to preshaking than VS, thus reflecting better the increase we see in liquefaction resistance over the long run? This should be the case because the CPT is more sensitive than VS to increases in relative density, and it's also more sensitive than VS to the lateral stresses that presumably also increase during the preshaking. But we wanted to check this conclusion in our own research. We did that by taking CPT measurements in the full-scale test we conducted as part of our 4 experiments. This experiment 4, done on clean sand at the University of Buffalo, in the 6-meter tall laminar box shown in the photo, where you can also see Dr. Sekelly, who is a tall fellow, despite the appearances. The 52 shakings are shown in the plot at the top, where we have plotted the peak base acceleration for each shaking, A sub PB. One difference with the tests I showed you before is that now we have some very strong event C, 1, 2, 3, 4, 5, 6, 7, 8 event C, which are the red lines, the red vertical lines. These are 15 cycles of 0.2 G. This is gigantic. And this event C always liquefy the soil. If you go to the bottom plot, you see the red open squares, and they are all at 1.0. They always liquefy the soil. The pattern of pore pressure in the bottom plot for RU-max is complicated, but in fact it also follows the same general rule of 2 steps forward, 1 step backward we saw before. As you can see, with the blue dots and the black dots at the end, they are much smaller than at the beginning. Okay? When everything is said and done, there was an increased liquefaction resistance. Now, the deposit was significantly densified by all these shakings. If you go to the second plot from the top, you can see that relative density at the beginning was less than 40%, and it was more than 80% at the end. And the third plot from the top, which shows the point resistance, normalized point resistance, Q sub C1N, it had a huge increase. It was about 17 at the beginning, and it was 130 at the end. This is a factor of 8. Let me walk you through 3 CPT profiles measured before 3 events B, immediately before 3 events B, using the pore pressure responses to those events B in order to show you how the liquefaction resistance was changing and how the corresponding CPT point resistance, and also the VS and the relative density were changing all at the same time. This is the first baseline CPT measurement done before any shaking, and immediately before the first event, which was an event B. The relative density was 36%. VS1 was 128 meters per second. The event B immediately afterwards did liquefy the deposit, RU-max equal 1.0. And to fix ideas, if you go to a depth of 2.5 meters, which is about mid-depth, the point resistance of the cone is about 500 kPa. Keep that in mind, 500 kPa. 30 events later, shaking number 30, the relative density has increased a lot from 36 to 74%. The shear wave velocity has increased a little bit, about 10–15%, from 128 to 148 meters per second. The deposit is now building up a very small pore pressure ratio of 0.1 for the subsequent event B, collapse from 1.0 to 0.1, which means it has a much higher liquefaction resistance. And the CPT at 2.5 meters has also had a huge increase in CPT. At 2.5 meters, it was 500 kPa, now it's 3,000. That's a factor of 6. And finally, let's jump to event shaking number 51 at the end of the experiment. Relative density has to continue to increase a bit from 74 to 83. Shear velocity is not changing anymore. Deposit again built up a very small pore pressure ratio, in this case 0.07, 0.1, instead of 1.0 at the beginning. And the CPT at 2.5 meters has continued to increase. 500, 3,000 is now 4,000 kPa, a factor of 8 compared with the initial point resistance of the CPT. Now, I am not saying that this factor of 8 between 500 kPa and 4,000 kPa at the end of the experiment necessarily represents the field conditions, as the measured CPT may have been influenced by the wall of the laminar box. But clearly there was a tendency for the CPT to increase very rapidly. And if the factor in the field is only 4 or 5 instead of 8, this still represents a huge increase in the CPT caused by soil densification and higher lateral stresses produced by the preshaking process. Therefore, this is our finding number 5, which is really a confirmation of what other people had already found and that we expected. The CPT point penetration resistance is much more sensitive than shear wave velocity to the increased liquefaction resistance due to preshaking. Let me add some concluding thoughts from this research. I'm down to my last 2 slides. I would like to make 2 general points in this first slide. My first point is a recommendation that we should start a systematic effort to measure directly the cyclic shear strain in the field during earthquakes as the sand layers build up pore pressures and trigger liquefaction by using existing or still to be built buried arrays of accelerometers and piezometers. The technology exists. Several groups have already shown how this can be done using system identification. And this would allow building up a database where pore pressure buildup is directly correlated to shear strain for future applications. We already know that pore pressures are more uniquely correlated to gamma sub C than to cyclic stress ratio. Therefore, let's put this knowledge to practical use. My second point relates to the use in the field of the cont penetration and shear wave velocity methods, which provide different pieces of information that complement each other. Even if a decision is made to use a VS chart for triggering evaluation, clearly the CPT provides additional key information to evaluate engineering consequences after triggering, at the very least. The best practice is just to measure both CPT and V/S. We are not alone in suggesting this. A similar recommendation has also been made, between others, by Dr. Schneider and Moss, and by last year's SEED lecturer, Dr. Peter Robertson. In this second and last slide of my presentation, my concluding thoughts have to do with the practical use today, immediately, and the immediate future of the CPT and VS to evaluate liquefaction triggering in the field. Based on our findings, these are our practical recommendations. For a silty sand, which is known to be an uncompacted recent field, give preference to the VS triggering evaluation over the CPT, as the VS chart works very well for uncompacted recent fields and does not require a fines correction. For older fields or natural sands with a well-known loading or preshaking history, we recommend, if possible, the use of either a CPT or VS regional chart, which has been calibrated by enough case histories, like the one we propose for the Imperial Valley. If there is a discrepancy between CPT and VS, give preference to the VS chart in order to avoid the fines correction. But if you know nothing about the sand history and no regional correlation is available, which I understand is the case today most often, use an available CPT correlation, as the CPT is much more likely than V/S to pick up the effects of the unknown loading and preshaking history on the liquefaction resistance of the soil. Thank you very much.